We're gonna try to resolve the three problems in chapter 5. The first problem is, suppose you have a shared memory tile with dimension 3232. Pat a column to it and then draw an illustration showing the mapping between data elements and banks for a Kepler device in 4-byte access mode. And actually, I have found a good picture for that, right? It's this picture from the internet. And this is what is 32 by 32, right? So, um, this is a how we call mapping between data elements. This is a data element and banks for Kepler device. This is a Kepler device of a type of GPU, but we want the shared memory tile with dimension 3232. So every single here, right? This is 32. This is 32. This is 32. Right? This is 32. So this is the dimension, and he's making it a square because is like is the same dimension. If it was like other dimension would be maybe a rectangle, but this is the same dimension, width and length. So we have in a square. So pretty much this is what it's hinting. What is it? 32 by 32. And then we have a next question is, suppose the size of a square shared memory array, check mem squared, was a 1616 instead of 3232. How would the number of shared memory transactions change on both Fermi and Kepler devices? Try to draw a picture of the shared memory arrangement in each case. So here, I found a good as well picture of this one, right? So here, we're going to try and read what the questions is. This is a 6 to 16 by shared memory, right? As we can see here, we have a 16 by 16, right? So here there's 4, 4, 8 plus 8, 16 is the same thing, which is a rectangle. How would the number of shared memory transactions change on both Fermi device? Try to draw a picture of shared memory. Right, so in here right now, we can see the shared memory, right? It's on 4-byte access device. So this is how the shared memory will go through this ones here. So for each thread on block, we have a whole shared memory, right? For each block dimension, there's going to be shared memory in between. And then ultimately, the global memory is going to be at the end, right? Like at the end in here. But for each block dimension, there is a shared memory between thread and blocks. And then ultimately, refer to the kernel. This is the code that we've seen before. Write the kernel using global memory to store the final difference equation and compare these three kernels. The kernel using a constant cache, the only using a cache, and the using global memory with L1 cache enabled. So this one here worked in this problem. And here we can see that we have this kernel, how it's going to look like. I grabbed that code from the book. And so here, this is just how we create the shared memory. This is the specific index ID. This is targeting a specific memory in an index. Here we have the boundary set up. And ultimately, when we're gonna do the unrolling, we're gonna through loop through whole memories, then installed output tap in here. So um, the main thing to grab from here, right, as we try and understand here, this is the kernel using global memory to store things, right? So this is a global memory because we use the share memory, and then we create like a kind of a this radius in here, right? So this one, what is make it target every single corner thread in the blocks, right? I mean, through the grid, there is the blocks and threads is going to target everything. This equation with the radius, it's like it can target any point, and this is what is making it a global memory. Thank you for watching.